Have you ever watched a game of Ultimate Frisbee taking place in the park? People moving all over the place, moving fast in every direction. The Frisbee is constantly moving from player to player. That rapid moving exchange between players and the Frisbee is a useful analogy for the processes in acids and bases, though we might need to add more Frisbees. Let me explain. This is Real Chem. There are many different acids and bases, so it can be confusing to sort out what's happening. But at its core, acid-base chemistry is just about proton transfer, one molecule passing a proton to another. You can think of it like a game of Frisbee, except instead of a plastic disc, we're tossing protons around. When we refer to a proton here, we're talking about H+ ions. A hydrogen atom is made up of one proton and one electron. So when the hydrogen loses the electron to form the H+ ion, it's just a proton. The key is to keep your eye on the proton, or the Frisbee. In a game of Frisbee, players are constantly passing the disc. Sometimes they have it, sometimes they don't. A player holding the Frisbee can pass it to someone else, while a player without one is ready to catch. As the game goes on, players keep switching between having and not having a Frisbee. Acid-base chemistry works the same way. Instead of Frisbees, molecules are tossing protons around. A molecule holding onto a proton is in its conjugate acid form, ready to pass that proton along. Once it gives the proton away, it switches to its conjugate base form, now able to accept one back. Now that we know how the game works, let's meet some of the players. First up, hydrofluoric acid, HF. HF is willing to toss its proton into play. When it holds onto the proton, it's in its conjugate acid form. When it gives it up, it becomes fluoride, F-, its conjugate base, ready to accept a proton back if the game calls for it. Now let's check out acetic acid, CH3COOH, the acid in vinegar. At first glance, it has a lot of hydrogens, but only one is in the game. That one labile proton or hydrogen ion is part of the carboxyl COOH group, the only location where acetic acid is willing to lose a proton. The protons that a molecule is willing to donate in acid-base chemistry are called labile protons. In its conjugate acid form, acetic acid, CH3COOH, holds onto its labile proton. When it loses that proton, it becomes acetate, CH3COO-, its conjugate base, now able to accept a proton back. To help keep track of acids and bases, we can use a simple particulate representation. We'll represent an acid as a box with a dot, where the dot represents the proton. The conjugate base is just the box without the dot, showing that the proton has been lost. We also indicate the charges on the base and hydronium ion, which result from the transfer of the positively charged proton. To show the electrons responsible for the bond, we draw a lone pair of electrons between the box and the proton. When the proton is lost, the lone pair stays with the base, so we include it in the particulate representation of the base as well. Now, this lone pair is important. It's like the hand of a Frisbee player. Just as the player uses the hand to catch a Frisbee, a molecule uses the lone pair to catch a proton. That brings us to ammonia, NH3, a molecule that plays the game a little differently. Unlike HF or acetic acid, ammonia doesn't have a labile proton to toss into the game. Instead, it's in its conjugate base form with a lone pair ready to grab a proton. When it does, ammonia becomes ammonium, NH4+, in its conjugate acid form. One of the main differences we need to consider here is charge. For HF and acetic acid, the conjugate acid form is neutral, and the conjugate base carries a negative charge. For ammonia, however, the conjugate base form is neutral, and the conjugate acid form carries a positive charge. This shift happens because ammonia is neutral in its conjugate base form and becomes positively charged in its conjugate acid form when it accepts a positively charged proton. But don't let these charges throw you off. Acid-base chemistry is all about proton transfer. When identifying conjugate acid and base forms, keep your eye on the proton, not the charge. So just like that game of Ultimate Frisbee in the park, acid-base chemistry is just a game of proton transfer. If we keep our eye on the proton, we can cut through the complexity and recognize conjugate acid-base forms with confidence.